Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it.
This is chapter 8. Um, and chapter 8 is integration techniques. All right. So let's start with some basic integration rules, which is what chapter 8.1 is. All right. Now, in here, the instructions are just evaluate the integral or find the integral. Evaluate the integral. So let's look at a couple of different integrals. So we have the integral of 9 over x squared plus 4 dx. All right, now if you recall from um, the last video, this actually becomes 9 times an integral of 1 over x squared plus 2 squared dx. And that is in the form of arctangent. So what we end up with here is 9 times arctan of x over 2 plus c. All right. I'm sorry, I forgot to do the over 2. Just 9 over 2. Arctan of x um, over 2 plus c. Now let's look at an integral that looks very similar. If I have the integral of 9x over x squared plus 4 dx, all right? Now this integral looks very, very, very similar to what we started with, right? The integral in part A. Now in this one, what I'm going to do here is I'm going to start with an u substitution. So we have u, and I'm going to let u be the entire denominator, x squared plus 4. Therefore, du would be 2x dx, so therefore dx is just du over 2x, right? At that point, what we can say here is that this integral now becomes the integral of, well, 9x. We didn't use that x in making our substitution. However, the denominator, x squared plus 4, that is our substitution. And then dx, well, dx was du over 2x. At that point, you see that the x's reduced. So what we really have here is just 9 times the integral of 1 over u du, which is 9 times ln of the absolute value of u plus c. And the problem was not about u, it was about x squared plus 4. So we have 9 times ln of the absolute value of x squared plus 4 plus c. All right. So a very similar looking integral, but very, very different way to attack the problem. Let's look at another one that looks still very similar. All right, so this is going to be example C. Let's say I had the integral of 9x squared over x squared plus 4 dx. All right, now in here, the very, very first thing you want to do is, well, what you'll note is that these are both polynomials. These are both quadratic polynomials. They're both of degree 2. When the degree of the numerator is at least as much as the degree of the denominator, your very first step should be to do long division, all right? Because we want to rewrite this. So what we're going to do here is we're going to take x squared plus 4 and divide it into 9x squared, all right? And then to do this, what we say, well, to do this division, we multiply by 9, so I get 9x squared plus 4, subtract. Not plus 4, plus 36. 9 times 4 is 36. There we go. And at that point we subtract, so I end up with negative 36. So what this tells me really is that my original fraction is equal to just 9 plus a negative 36 over x squared plus 4. At that point, I can say, well, that means that this original integral can now be rewritten as the integral of 9 minus 36 over x squared plus 4 dx. And I could turn this into two integrals, the integral of 9x, excuse me, the integral of 9 dx, and minus 36 times the integral of 1 over x squared plus 2 squared dx. And that will give me now, well, the integral of 9 dx is 9x minus 36 times the integral of 1 over x squared plus 2 squared. We just did that, right? We had a different coefficient in example A. That's essentially what we had, right? Just with a different coefficient. Instead of a 9, now we've got a 36, right? Excuse me, a negative 36. So in here, what we end up with is 1/2 arctan of x over 2 plus c. So I can write my final answer as 9x minus 36 times 1/2 is 18. And we end up with arctan of x over 2 plus c. Now, that was doing long division. And again, that you would do long division whenever we have the polynomial on top being at least the polynomial on bottom. So for example, if this was 9x cubed, I would still start off with long division, all right? Now, that was C. Let's redo C, but in a different way. So I'm going to call this C star, all right? So we have, again, the integral of 9x squared over x squared plus 4 dx. All right, so another way to look at this integral is if we rewrite this as 9 times the integral of x squared over x squared plus 4 dx. All right, now in that format, what we can do is we can rewrite this fraction by adding 0. All right, so let me show you what I mean. So I have 9 times the integral of x squared plus 4 on the bottom dx. And now let me add the 0. The 0 that I'm going to add here is a plus 4 minus 4. All right, adding 4 and subtracting 4, that's just adding 0. It doesn't change anything. Now, why would we want to do that? Well, at this point, let's see what our integral becomes. It becomes 9 times the integral of, well, I'm going to split this fraction up in this format. X squared plus 4 over, excuse me, the fraction. So yeah, so over x squared plus 4 minus 4 over x squared plus 4 dx, which really just says that this is the integral of 9 times, so 9 times the integral of 1 minus 4 over x squared plus 4 dx. If I throw the 9 back into the integral, what I really have is the integral of 9 minus 36 over x squared plus 4 dx. And you should recognize that because that's exactly what we had up here, right? 9 minus 36 over x squared plus 4 dx. But we know what that becomes now. So that's 9x minus 18 arctan. So this is 9x minus 18 arctan of x over 2 plus c. So we got the same solution, which is good, right? Because it's the same problem. But what I wanted you to see there is just an alternative to having to divide, all right? Now, this alternative only works when you have the degree on the numerator and the denominator being the same, all right? Um, and you would only be able to add 0 on numerator stuff, all right? But anyway, so let's do D. D is the next one. So D is the integral of 3 over the square root of 4 minus x squared dx. All right. Recall when we were covering integrals involving inverse trig This right here is in a very specific format. It's one of those. All right, so I can rewrite this as 3 times the integral of 1 over the square root of 2 squared minus x squared dx. And that is in the form of arcsine. All right, so in here, what we really have is 3 times arcsine of x over 2 plus c. All right, now let's look at another one that looks very similar to this. So e, the integral of 3x over the square root of 4 minus x squared dx. All right, so in here, the very first thing I'm going to do here is I'm going to do a u substitution. All right, and in here, I'm going to say, well, let u be equal to 4 minus x squared. That tells us that du would be negative 2x dx. All right, notice that I already have an x dx over here. So what I can do here is I can solve for that on the right hand side, and I end up with du over negative 2 is equal to x dx. So that would allow us to replace that. So now let's go ahead and make our substitutions. Our integral now becomes, well, this 3x, well, the 3, we didn't use it for anything, so the 3 is still there. This x dx, we just said becomes du over negative 2. So I have du over negative 2. And then this square root of 4 minus x squared, well, the square root, I'm still going to write it there as a power to the 1 half, but the 4 minus x squared, that was our u. So what we really have here is negative 3 halves integral of u to the negative 1 half du, all right? And at that point, it becomes very simple to integrate. So we add 1 to the exponent, so we still have negative 3 halves. So negative 1 half plus 1 is positive 1 half. Divide by the new exponent means multiply by the reciprocal. And then we have that plus c, giving us our final answer of negative 3, right? Because those 2's cancel each other out. So we have negative 3 u to the 1 half plus c. But the problem was not about u. The problem was about x over here, 4 minus x squared. So 4 minus x squared. There we go. All right. And that would be the final answer for that integral. All right. Um, now, if I were to follow the same kind of pattern that I did with the previous 3 examples, the next one would logically be the integral of 3x squared over the square root of 4 minus x squared dx. However, we don't have the tools to do this yet. We'll do this when we get to 8.4. All right. But there is a way to do this kind of integral. All right. Now, next example. Let's move on to to G. Let's say that I had something that looks similar to this. So I'm going to have now the integral of 3x squared over the square root of 4 minus x to the 6th dx. All right. Now, notice that I've got a 4 minus x to the 6th on the bottom. But what I want you to focus on is on that x to the 6th. When we have things like that, we can manipulate them, right? And by that I mean 6 can be rewritten as 2 times 3. It could also be rewritten as 3 times 2. Why do I care about that? Well, because I can manipulate things to write them in such a way. X to the second to the third is still x to the sixth. X to the third to the second is still x to the sixth. So we can manipulate them this way if we needed to, right? We can also do things like x to the 1/3 and then to the 18. That's still the same as x to the sixth, right? Um, it's not as easy to see that last one, but the idea here still stands that we can rewrite x to the sixth in many different ways. So we're gonna actually do that in this specific example. What we're gonna say here is we're gonna rewrite this as the integral of 3x squared over the square root of 4 minus x to the third squared dx. And the reason for that, for choosing it this way, is because I see that down here, if I end up with this x cubed, if I take the derivative of that, I have it on the numerator, 3x squared. But not only that, I see that I end up with a difference of squares inside here. All right, so that is super helpful as well. So let's see what this gives us. So if I set u to be x cubed, then du would be 3x squared dx, which is right there. So we can replace that right away. So what we end up with now is, so that entire numerator with a dx, that is our du. On the bottom, I've got the square root of 4 minus u squared. All right. Now this one you should recognize. All right. This one right here is essentially example D, right? It's with a different coefficient. We've got 3 there, but it's essentially the same format. So what I can say now is that this becomes just arc sine of u over 2 plus c. But we know not to leave our answers in terms of u, so it's arc sine of x cubed over 2 plus c. All right, next one. So that was G. H. Let's say that I had something like the integral of 4 over 4 plus e to the x dx. All right. Now, in here, there's multiple ways of approaching this one. The most common way that people try to approach it at first is to say something like, let u be equal to the entire denominator, 4 plus e to the x. That would give us du being e to the x dx, right? Now, if we do that, let's see what happens here. Well, we end up with this integral of 4 over that 4 plus e to the x. That was our u. So 4 over u. This dx, well, let's solve for dx here. So if I solve for dx there, what I have is du over e to the x. So I'm going to write that down over here. So instead of dx, I've got du over e to the x. But there's a problem with that because we still have x's. So we can do here from this statement, we can say that e to the x is u minus 4. All right. So what we can do now is we can rewrite this as u minus 4. Well, let's write that in white. U minus 4. There we go. So that's what we end up with there. So this would be the integral of 4 over u times u minus 4 du. Now, as written, we still don't have the tools to answer that kind of question. All right, there is a way to answer this exact kind of integral, but we have not covered that. That is in 8.5. So let's look at how we can solve it using other methods that we have spoken about. All right. So again, in here to continue from here, you will need a tool from 8.5 to be able to use it to do that. So let's see how else we can manipulate this. So I have 4 over 4 plus e to the x dx. All right. One of the things that we spoke about earlier was adding 0. So that's exactly what I'm going to do in this case. I'm going to add 0. And that 0 is going to be e to the x minus e to the x. All right. So I'm adding e to the x minus and subtracting e to the x. So that right there is just 0, right? So that doesn't change anything. But what we can do is we can manipulate this fraction to be the integral of 4 plus e to the x over 4 plus e to the x minus e to the x over 4 plus e to the x dx. At that point, this first fraction just becomes 1. And the second fraction, so let's split this up into two integrals. So I get 1 dx minus the integral of e to the x over 4 plus e to the x. And that was supposed to be an exponent. Dx. All right. Now that as written, now we can actually um, go ahead and work this one out. All right. So what we can do here is in the second integral, we can do a u sub. So let's make u be our entire denominator. At that point, our du would be e to the x dx. How convenient. We have that e to the x dx right there. So what we can do now is we can say, well, this was just the integral of 1 dx minus, and we have this other integral, 4 plus e to the x, and that was our u. E to the x dx, that was our du. So we get 1 du. At that point, we would say, well, this just becomes, in the first one, I'm integrating with respect to x, so I just get x minus. In the second one, I'm integrating with respect to u, so I end up with ln of the absolute value of u, all right, plus c. But we know that we cannot leave our answers in terms of u, so we have x minus ln of the absolute value of 4 plus e to the x, and then that plus c, all right? Now, there's more ways to answer this kind of question. So I'm going to do it in one more way. All right. So I guess I should have labeled this one H star, and now the next one is going to be H double star. So in here, I'm going to work with this. So the same integral. So we had the integral of 4 over 4 plus e to the x dx. All right. Now, with any math problem, we know there's always two things we can do. We can add 0, right? Just like we did in this previous version, or we can multiply by 1. In this case, I'm going to multiply by 1. But that 1 is very difficult to see in this specific scenario. I'm going to multiply by e to the negative x over e to the negative x. All right. What does that give me? That gives me the integral of 4e to the negative x over 4e to the negative x plus 1 dx. All right. Notice that when I multiply e to the x times e to the negative x, well, same base, different exponents, add the exponents. X minus x is 0, so e to the 0 is 1. All right. So maybe I'll write that real quick. So e to the x times e to the negative x is e to the x minus x is e to the 0 is 1. All right. Now, let's move that aside. Well, that's not what I meant to do. Ah, that's not what I meant to do either. Where is it? There it is. There's the select button. All right, so now that was just some side work. Now, in this integral that we have over here, what we can do is we can do a u substitution. Let u be the entire denominator, 4e to the negative x plus 1. Then at that point, our du would be negative 4e to the negative x dx. All right. Recall that the derivative of e to the negative x is negative e to the negative x because of the chain rule. So that's where that negative came from. Now, look how convenient we have that right there. We have 4e to the negative x right there. So what we can do is say that negative du is 4e to the negative x dx. So what we have now with this integral, we can say that it becomes, well, I'll continue down here. It becomes the integral of, well, what was our u? Our u was the entire denominator. Cool. So our entire denominator is u. The 4e to the negative x dx, we just said that that becomes negative du. So we have negative du. So at this point, this becomes the negative integral of 1 over u du, which would be negative ln of the absolute value of u plus c. But we know not to leave our answers in terms of u. Our u in this case was 4 times e to the negative x plus 1. So we end up with negative ln of the absolute value of 4e to the negative x plus 1, and then that plus c. But now, that is not the same answer we had before, right? That's not the same answer we had before. Look at this. We have x minus ln of 4 plus e to the x. So let's see where we went wrong. Well, in fact, we didn't go wrong anywhere. What we can do here is we can rewrite this. So we can rewrite this as negative ln of the absolute value of 4 over e to the x plus 1. Coming up with a common denominator, I end up with, let me just shift that a little bit. I'm going to shift this all the way over here. There we go. And so coming up with a common denominator in there, I end up with negative ln of the absolute value of 4 plus e to the x over e to the x plus c. Using rules of logs, this can be rewritten now as negative ln of the absolute value of 4 plus e to the x and minus ln of the absolute value of e to the x plus c. Notice I put those brackets there. I put those brackets there because this negative sign that's on the outside has to apply to everything inside here. When we do that, well, what do we get? If I distribute the negatives and simplify this, notice that this statement, ln of e to the x, is just x. And if I distribute this negative, well, I end up with negative times a negative is a positive. Negative times a positive is a negative, so x minus ln of the absolute value of 4 plus e to the x plus c. So it kind of looked like we had gotten the wrong answer, but it turns out that we didn't. It was the correct solution, all right? So you have to be careful with problems like these, all right? Because when you were to check it on the back of the book or something, or maybe you check it online somewhere, you might not get the same exact solution that the other person might have gotten, but that's because you might have done it in a slightly different way, but it turns out to be an equivalent solution. All right. So keep that in mind that there's multiple ways to solve the same integral, and the answers, the final answers, may not necessarily look the same. All right, next example. I. Let's say that I have the integral of tan of x times ln of the absolute value of cosine of x dx. All right, so here, the big giveaway here that we should be using um, a use substitution is that ln of absolute value of cosine of x. All right, if you recall, we we discussed at one point what the integral of tangent was. All right, so the integral of tangent was ln of cosine of x. Excuse me, negative ln of cosine of x. There we go. And well, let's see what how we're gonna tackle this. So because of that, because the integral of tangent is that, I recognize that we're gonna need to use this as our u. So let's go ahead and do it. So we have u is equal to ln of the absolute value of cosine of x. So that tells me that du would be 1 over cosine of x times negative sine x dx. So this really is just du is negative tan x dx. And again, in here, I got 1 over x because the root of ln of something is 1 over that thing. And then by the chain rule, that's how I get that negative sine x over here. All right, so now that allows us to rewrite this, right? Our u was ln. Um, and by the way, notice here that I have this tan of x dx, tan of x dx. How convenient. So what we're going to say here is that negative du is just tan of x dx. All right, and that I'm going to change the color. There we go. So now this tan of x dx, we just said is going to become negative du. This ln of cosine of x, that's our u. So what we're going to say is that we have u times negative du. So what we really have here is negative integral of u du, right? So at this point, well, what is the integral of that now? Well, it becomes negative u squared over 2 plus c. So we know not to leave our answers in terms of u. Our u was ln of cosine of x. So we have negative ln of the absolute value of cosine of x squared over 2 plus c, right? And we would leave it as that. There's nothing else that we can do there to manipulate it in any way. So that was I. Next one, J. So here we go, J. And here I have the integral of tan squared of 3x dx. The very first thing I want to do here is I don't want to work with that 3x. So I'm going to do a u substitution. Let's get rid of that. So let's say that u is equal to 3x. Therefore, du will be 3dx. And at that point, we're going to say, well, let's make let's go ahead and replace those things, right? Because from here I can say that dx is du over 3. So I'm gonna have this integral now. This integral becomes, well, that tan squared we didn't use for anything, so that's tan squared. That 3x, that was our u, all right. And then that dx is du over 3. So I'm just gonna rewrite this as 1/3 integral of tan squared of u du. All right. Let's just rewrite that integral sign. There we go, way better. Now, at this point, well, what can we do? Now, it's common to think that we can do another u substitution, right? It is technically a legit method of trying to continue here, but it would not be useful. People think that you can do a u substitution with tangent, but the thing is, we don't have the du there. By that I mean the dv. So by that, so let me show you what happens when you try to make another u substitution. If I let v be tangent of u, then dv is secant squared of u du. The problem here arises when we try to replace that du. We don't have anything with a secant squared. But the one thing that we can do is we can recall Pythagorean identities. All right, this is from pre-calc. Recall that if I have sine squared, well, that's not what I meant to write. If I have tan squared theta plus 1, that's equal to secant squared theta. All right, tan squared theta plus 1 is secant squared theta. So that really tells me that tan squared theta is equal to secant squared theta minus 1. So I'm going to use that to rewrite my integral. So what I have here is 1/3 times the integral of secant squared theta minus 1. Not theta, we were using u. There we go. Secant squared of u minus 1 du. And from there we'll say, well, that gives us 1/3 times the integral of secant squared. The integral of secant squared is tangent, right? Because the derivative of tangent is secant squared. The integral of 1 is just u, because we're integrating with respect to u. And then we have that plus c. But then we know not to leave our problems in terms of u, our final answers, I mean. So we have 1/3 times tangent of, what was our u? Our u was 3x. So tangent of 3x minus 3x plus c. All right. Oh, look at that. This 1/3 should be multiplying everything here. So I really should have the multiplying everything there. So when I do that, I end up with 1/3 tangent of 3x minus x plus c. There we go. Much better. It's way better when it's correct. All right, so that's the final answer. And that was J. So next one, K. K is the integral of 1 over cosine of theta minus 1 d theta. All right. Now, again, this is something that people think that you can do a u substitution with, but you can't. Let me show you what happens. If I take u being that entire denominator, then du would be negative sine theta d theta. So here is the problem. You can't replace that sign. It's not going to go away. All right, it doesn't exist anywhere here. So we're not going to be doing a U substitution. All right. So what are we going to do instead? Well, instead we're going to multiply it by 1, and that 1 is going to be the conjugate of the denominator, all right, over itself. So notice that that fraction is just 1, right? So what does that do for us? Well, that gives us the integral of cosine theta plus 1 on the numerator, and the denominator, I've got the product of conjugates. The product of conjugates is the difference of squares, but make sure you keep it in the order that it was given, all right? Now, I've got that cosine squared minus 1 on the denominator. From the Pythagorean theorem, from the Pythagorean identities, we also have that sine squared theta plus cosine squared theta is equal to 1. So if I move the 1 over and the sine squared theta over, that gives me that cosine squared theta minus 1 is equal to negative sine squared theta. I move the 1 to the left and the sine squared to the right. Right? So what I can say now is that this integral is just the integral of cosine theta plus 1 over negative sine squared theta d theta. Now this negative on the bottom, it doesn't need to be there. I can put it on the outside and get rid of it on the bottom, right? Now in here, in that statement, now that I've got this cosine theta plus 1, all right? You know what? Let's split this up. Let's split this up. So we have the negative integral of cosine theta over sine squared theta plus 1 over sine squared theta d theta. When we do that, what do we get? We end up with the negative integral of, well, cosine over sine squared. Cosine over sine squared can be written as cosine theta over sine squared theta. That's not rewriting it. Cosine theta over sine theta times 1 over sine theta. And then we still have a plus 1 over sine squared. Well, 1 over sine squared can be written as cosecant squared theta. Now, let's distribute this negative. So, and rewrite this. So I'm going to have the integral of negative, well, cosine over sine is cotangent theta. 1 over sine is cosecant theta. Distribute the negative to the other one, I end up minus cosecant squared theta d theta. And those are integrals that you should know. All right. The integral of negative cotangent cosecant is just cosecant theta. The integral of negative cosecant squared is just cotangent theta. So that is our final answer, cosecant theta plus cotangent theta. All right. And you should know those because you should know the derivatives of cosecant. The derivative of cosecant is negative cosecant cotangent. The derivative of cotangent is negative cosecant squared. All right. So that's why you should know those. Now that is the end of 8.1. One thing that I want you to really take away from 8.1 is that there are some problems that can be done in multiple ways, all right? And there are other problems that can't, all right? But at the same time, you should start to get a feel for which kind of method you can do with some of these integrals, all right? Whether you need to manipulate it or whether you need to do a U sub, all right? There's multiple ways to attack a problem. All right, that is the end of 8.1.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.